And Jeremy will give a talk about digestibility problems in black soldier fly larvae. His talk is entitled as Filling a Gap in Diet Formulation Approach, How to Assess Digestibility in Black Soldier Fly Larvae. So before Jeremy starts, I would like to indicate that he has a PhD thesis on this aspect, a very nice PhD thesis. And I was just going through this PhD thesis, and I saw a very nice illustration by himself. So I give you maybe a little bit of time until you go through it. So it shows very nicely his motivation and as inspiration also why he's working on black soldier fly and particularly with black soldier fly larvae thesis. It's a very nice illustration, and the whole PhD thesis as well as the illustration in the PhD thesis is available online. And before Jeremy starts, I also would like to say he kindly agreed to make his slides available already, and I put them in the shared folder of Working Group 5, so you can now even have access to it. And just very briefly, I would like to introduce Jeremy to you. So he's working at AgroNutrients in France as a research and development project manager. He did a master thesis on livestock production, and his PhD thesis focused on black soldier fly larvae nutrition, mainly on digestibility assessment. It is available online also. You can, I put there also a link. You can really have it also. And he is now working at AgroNutrients, which is a company that deals with black soldier fly larvae to produce insect-based ingredients for animal nutrition. And the company is located in Rethel in the east of France. And I think we can now move to the presentation. So I thank Jeremy once again. We had a very short talk before we started this meeting today. So I appreciate very much. Actually, he did spent a lot of time to prepare his presentation, and also he will be giving a talk about, I think, 45 minutes. We will have quite good time, and then we can also have questions and nice discussion around the topic. So Jeremy, the stage is yours now. I will stop sharing my screen. Maybe then you can start it.
Yeah, thanks a lot. Thanks a lot, Gerbus, and also David for inviting me. So I will share you my screen. In the meantime, I have to tell you the truth. I am not the one who drew the drawing that was just presented. It's a friend of mine who did it, but I really like it. And it was included in my PhD thesis as a short introduction. What do you see?
I see your presentation.
Like in full screen?
Yes.
Okay. So give me just one moment, because I'm not seeing it. I don't understand what's going on.
Oh.
Okay. Do you still see it in full screen?
Yes, we see it.
Okay, that's perfect. Okay, so thanks a lot, Gerbus, for the introduction once again, and thanks for inviting me. So I will not introduce myself once again. You already said what needed to be said. So today we're going to talk about digestibility, why it's important, why we want to work on it, and what remains to be done on these aspects in black soldier fly larvae. So you probably already know that these black soldier fly larvae have a very highly versatile feeding regime, which is of course a strength when we want to valorize different types of waste, but it's also a challenge because this variability of feeding regime is also associated with a variable output of the larvae. That is to say, a variable zootechnical performance in terms, for example, of individual weight, protein content, etc. And this is a challenge, especially in an industrial context, such as the one of AgroNutrients. So what we are doing is that we are trying to deal with a varying input, which is the feeding substrate that varies in quality in terms of seasonality. The quality of the agricultural byproducts can vary depending on from one year to another, etc. And still, we have to cope with this variability to produce a stable output in terms of larval zootechnical performance and black soldier fly larvae meal quality. We want to provide our customer with a quality of meal that is stable. So that's an issue, especially when and this variability can be represented with this figure. So when we're using one type of bio waste as a substrate for black soldier larvae, we'll have a strong variability of the larval performance. So what is usually done is that we can mix and perform use different combinations of bio waste in order to have a more balanced nutritional composition, and this will generally be associated with an improved performance and a reduced variability of the zootechnical performance, but the variability is still very, very significant. So this is what I would call empirical formulation. It's just trying to find the right combination of bio waste without having a look at the nutritional composition. So of course we can go a bit further and work and consider the nutritional composition of the diets in order to reach the requirements, which is, I guess, the requirement definition, I guess, has been debated during the previous webinars. Unfortunately, I didn't attend to it. So when we consider the crude nutritional composition, such as protein and carbohydrate, for example, we can define isonutritional diets, and these isonutritional diets are associated with a lower intra-diet variability, but there is still a significant variability between these isonutritional diets. And one possible explanation for this variability is that although we have the same amount of crude nutrients in the different diets, it is not digested in the same way. So that means we need to consider digestibility to have a more accurate and a more precise diet formulation approach. So what exactly is digestibility? What do we mean when we talk about digestibility? So it's a very usual metric used in conventional livestock species. So in this presentation, I will often refer to conventional monogastric animals, and I will take the example of swine. So here you can see the breakdown of distributed feed in swine, and considering these different flows, these different nutritional locations, we can have different definitions of digestibility in swine. So here I give you two examples. So first of all, here you see my pointer. So when the feed is distributed, it will be partly ingested and partly refused, and the part that is ingested, part of it will be hydrolyzed and then absorbed by the animal and then metabolized and used, and part of it will not be absorbed, or sometimes also not hydrolyzed. This part will constitute what we call the exogenous feces, so the feces coming from the feed. And I make this detail to this point because we also have endogenous feces that come from the animal itself, or from the microbes that are in the digestive tract. And these two flows constitute the feces that will be released in the environment. So this is quite straightforward to measure what we call apparent digestibility in pigs, just by considering the amount of feed that has been ingested by weight difference between what has been distributed and what remains in the end, and the weight of feces. It's quite straightforward. And we can go a bit further by defining true digestibility, which is quite similar, except that we have to remove the endogenous feces. So even for pigs, there are different ways of assessing and way of defining digestibility. And this definition issue is really what will drive this presentation, because we'll see that it's more complicated in insects and even more complicated in black soldier fly larvae. So in conventional livestock species, the most straightforward way to measure digestibility is the gravimetric method, which consists of total feces collection. So our predecessors, scientists who worked on conventional livestock digestibility assessments, developed different approaches to manage to collect all the feces associated with a certain amount of ingested feed. So here you see, for example, a digestibility stool for pig that allows a complete feces collection. You have an example of what can be used in cattle with a cow equipped with bags that allows to collect separately the feces and the urine. And in fishes, we had to, researchers had to come up with even more complex solutions. And you can see on this picture, on this drawing, that one of the solution that was imagined is to use a tank where the feces can be collected by decantation, sorry. And so this is the kind of approach that we would like to develop for black soldier larvae. But as I mentioned, things are much more complicated in black soldier larvae. So this is the same figure as before, but the differences with the pigs have been are highlighted in red. So the first difference is that the non-ingested feed, the part of the feed that is refused by the larvae, will be mixed with the excreta to form frass. So frass is a mixture of both. And that means that, first of all, we will not be able to assess the amount of feed that has been ingested. And this is going to be extremely tricky to measure digestibility later on. Second, we have to highlight that excreta, so I talk about excreta and not feces anymore, because excreta is a mixture of feces and urine. Indeed, due to the digestive physiology of insects, the excreta is a mixture of feces and urine. This is something that they have in common with poultry. And that means that we will not be able to measure what has been defined as apparent digestibility in swine. We'll have to come up with a different definition and a different approach. So same for true digestibility. It would be even more complicated to assess true digestibility in black soldier fly larvae. So those two terms, in my opinion, should be avoided. And actually, it's not only in my opinion. There is a very nice paper from Waldbauer in 1968. So it's quite old, but it's still very relevant in my opinion. I will give the reference in the end. This paper from Waldbauer gives detailed definitions of different digestibility indicators in insects. And I think it's extremely important to be clear on what we call digestibility when we are working on these aspects. There are a few more differences between black soldier larvae and pigs in terms of digestibility. So first, the frass also contains exuviae and dead larvae. So this can have an impact when we want to work on these aspects. Frass can be possibly ingested multiple times, which will likely enhance the digestive efficiency of the system. And last but not least, in pigs, the microorganisms have a role in digestion only in the digestive tract. But as you know, in black soldier fly larvae, the microbiota is also active directly in the substrate. So both in the substrate and in the digestive tract. And these are major differences that we have to take into consideration when interpreting our data. So as I said, the definition of apparent digestibility in swine is not applicable with black soldier fly larvae, but we can define a proxy of digestibility, and this is what I call estimated digestibility. So estimated because we will not consider the amount of feed that has been ingested, but the amount of feed that has been distributed. And we will not consider pure feces, but we will consider frass, which is a mixture of different things, as I mentioned before. However, this definition, for it to be reliable and to be to truly account for what is digested by the larvae, we need to work in certain conditions, and we need to make sure that the amount of feed that is distributed is that mostly all the feed that has been distributed is ingested by the larvae. So how to reach total ingestion? This was one of the main questions that I explored during my PhD thesis. And we came up with two different solutions. The first one is to increase larval density up to a certain level where we can assume that everything has been ingested. And the second approach was to increase feeding time. Same idea. At some point, we can assume that everything has been ingested by the larvae. So I will detail these two methods. The first one, so as I mentioned, our hypothesis was that for the same amount of distributed feed, the more larvae we add in the system, the more the substrate will be ingested. So that ultimately, all the feed that has been distributed has been ingested, and we will get frass that is completely free from non-ingested feed. And as a result, we were assuming that the estimated digestibility will increase with larval density up to an asymptotic level. So we called it asymptotic estimated digestibility, which represents the maximal potential that black soldier fly larvae and the associated microbes can digest in the system. So we challenged this approach and we tried it. So it's quite an obvious setup. So we used the starter larvae, same substrate input as I mentioned, but a varying number of larvae. The graphs after will be presented in terms of larval density by area, so larvae per square centimeter. We used from 0 to 29 larvae per square centimeter. At the end of the trial, all of the frass was collected in order to perform nutritional analysis on the frass and to have a mass balance approach between the feed that has been distributed and the frass that remains in the crate in the end. The end of the trial was defined at as the moment where the crates with the highest larval density could be sieved. So this is something that might need refinement for future studies because this period of time can vary from one substrate to another, of course. And this is the kind of results that we obtained. So here you can see that with an increasing areal density, so an increasing larval density, you get an increasing estimated digestibility of starch up to an asymptote. So, and this pattern was modeled using a logistic model, and we identified that the asymptotic estimated digestibility of starch in chicken feed, which was the standard diet that we used for developing the approach, the value was 99.3%. So a very high digestibility of starch in chicken feed for black soldier fly larvae. We used the same approach for two byproducts more relevant for an industrial application, which were corn gluten feed and discarded potatoes. And we observed this similar pattern. So an increase of estimated digestibility up to an asymptote. And the asymptotic values were 100% for corn gluten feed and only 84% for discarded potatoes. So we can see differences in digestive efficiency in black soldier fly larvae for starch. The same approach was used for protein. So you can see the results here. And once again, we observed this similar pattern, the asymptote, and we were able to assess the asymptotic estimated digestibility of protein for these three diets. So there are more data in a paper and in my PhD thesis manuscript, which both are available online. But I will only focus. I will not go deeper into the details. The idea was just to present you the method. So these coefficients could be used as digestibility coefficients for formulation. So as I mentioned before, we also had another idea. It was to work with an increasing feeding time instead of an increasing larval density. So here the approach was to work with the same amount of substrate and the same larval density, except that there are some crates that we will harvest earlier and some others that will be harvested later. And our hypothesis was that we will have an increasing estimated digestibility up to an asymptotic value that would represent the maximal digestion capacity. So here is the result that we obtained on chicken feed for starch and for protein. And once again, we have this asymptotic increase that confirms our hypothesis. Then we compared the values that we obtained with the increasing larval density and the increasing feeding time approaches. And you can see that the values are very close. So we consider that this method might be truly relevant for digestibility assessment in black soldier fly larvae. There is, for those of you who are familiar with digestibility assessment in conventional livestock, you very likely know that we can also use an indirect method to measure digestibility. That is to say, not the gravimetric nutritional balance between ingesta and feces approach, but an indirect method using an indigestible marker. So we wondered whether we could also use this approach for black soldier fly larvae. So the idea of this method is to incorporate an indigestible marker in the substrate. This marker will have the same quantity in the ingesta and in the feces, but it will be more concentrated in the feces because part of the feed has been digested. And based on this marker conservation, we can find a simpler way to calculate apparent digestibility in conventional livestock. I say simpler because we will require concentration of marker. That means we only need a sample of feces and a sample of the feed to perform on our analysis. We do not need anymore to have an exhaustive feces collection. Different types of indigestible marker can be used. They can be initially present in the substrate. It is what we call endogenous markers, such as lignin, silicon, etc. Or they can be added artificially in the substrate, such as different types of oxides. So what about black soldier fly larvae? On paper, it works similarly, except that, as I said in the introduction, we will not collect feces, but excreta, which is a mixture of feces and urine. And as a result, what we will measure cannot be called apparent digestibility. If I refer to Waldbauer, this should be defined as approximate digestibility. So I did not come up with this name. This is something that was already documented in previous papers in other insects. And here we now need to find a way to collect excreta, to collect a sample of excreta, not frass, but true and pure excreta. So we had different ideas. I don't know if you knew it, but the excreta of black soldier fly larvae is most of the time liquid. So it looks like this, but I also observed that when after starvation period or when the substrate is when the frost tends to be drier, you can have something solid that we can see on this picture. So we wondered what was the simplest way to collect pure excreta from the larvae. We had this idea to use to immobilize some individuals in pipette tips, or to use the diapers that have been developed by Moritz Gold and collaborators. But in the end, both these methods were really impractical, time-consuming, and we collected very little material, so it was impossible. To clean the larvae. Do you still hear me? I have a notification by Zoom. Gerbus, can you confirm that you still hear me?
Yes, we can hear you.
Okay. Okay. Well, there was something surprising, but
totally, yeah.
so yeah, the up with, is it still good? Yeah,
it is good.
Okay, thank you. The solution that we came up with was to clean the larvae and place them in an empty clean container to let them defecate for 24 hours in order to be able to collect the excreta. So the general overview of the materials and methods, we included chromic oxide as an indigestible marker in the substrate. So this is a marker that is responsible for the green color of the substrate that you see here. We let the larvae eat for a few days, then we remove them from the substrate, we clean them, place them in an empty container, as I said, and for 24 hours, we let them defecate. Then to collect the excreta, we had to dilute it in distilled water in order to be able to collect it with a pipette. After that, the water was evaporated. And finally, we were able to quantify the amount of the concentration of chromic oxide in the excreta by spectrophotometry. So this is the results of approximate digestibility of dry matter that we obtained for the three substrates that I mentioned before. We only have results for dry matter digestibility. because the amount of excreta that was collected was too little to perform analysis of starch or protein contents, unfortunately. So once again, this method needs some refinement in order to be able to collect more material and perform deeper analysis. If we compare the results with the first approaches that I presented, so the asymptotic estimated digestibility of dry matter, we can see that the order of the substrates remain the same, but asymptotic estimated digestibility is always lower. So we wondered why we have this quite important difference, especially in corn gluten feed. And one possible explanation that we came up with was that the larvae might not actually ingest all the particles, all the feed particles. So the approximate digestibility approach assumes that the marker concentration that is included in the feed is the same as the marker concentration in the part of the feed that is ingested by the larvae. But should we assume that the marker is in the liquid phase of the substrate and we have small particles and bigger particles? If everything is eaten, then the approach is reliable. But if the larvae refuse to eat the biggest particles, then the marker is more concentrated in the part of the substrate that will be ingested, which will lead to an overestimation of approximate digestibility. So this might be why we have a much higher value of approximate digestibility compared to asymptotic estimated digestibility of dry matter. So to conclude, we developed 3 different methods. And I will briefly go through the pros and cons of the three of the methods. So the first one was asymptotic estimated digestibility with the increasing larval density. One upside is, of course, the way of rice that we collect that is enough to perform various nutritional analyses. But there are some downsides. The first one, and it's quite significant, as I mentioned, all the crates need to be harvested and sieved on the same day in order to work in similar conditions. And the only parameter that varies is the larval density. And it results in quite a significant workload. So this is something to have in mind should you perform this kind of approach. And second, we have to use extreme larval densities in some cases in order to reach total ingestion and to perform the approach. And this extreme larval density could be stressful for the larvae and could, of course, have an impact on digestion, which is something that we cannot see with this approach. The second approach, asymptotic estimated digestibility with increasing feeding time. So we have the same upside. It's quite easy to perform various nutritional analysis. But should we use this approach with poor performing substrates, substrates where that induce mortality or where the larvae grow very poorly, very slowly? That means we will have a very long time before reaching the asymptote and reaching the total ingestion of the feed. So this approach is not reliable for this kind of substrates. And finally, when we want to design a trial with this approach, we need to know when will be the final day of the experience, when the last crates will be sieved. That means that this approach requires most of the time a preliminary trial in order to properly design the experience. And for the third approach, the approximate digestibility with an undigestible marker, it requires less experimental units, so less crates than the other methods, and a shorter rearing time, shorter rearing time. And this approach will only consider the digestion that occurs within the gut and not in the substrate, while the 2 others will consider the overall digestive efficiency of the system, both the larvae and the substrate. But the downside is that, as I said, we collect very little material. It is inaccurate if the larvae are selecting what they want to eat and what they don't want to eat and refuse the biggest particles. There is a starvation step for feces collection, which can also be stressful and have an impact on digestion. And last but not least, the marker that we use was chromic oxide, and it has been criticized over the past decade or even more because the way we quantify it as an impact on the environment, and we should probably switch to a more environmental friendly and digestible marker. The reason why we used this one in the first place was that it was because we could find different papers that were using this marker on insects. So we wanted to use the same approach as in these papers, but they were quite old papers from the 60s, 70s, or 80s. So we should probably update this approach. So what is my recommendation? Should you want to work on digestibility assessment in black soldier fly larvae, I would suggest you to go with the asymptotic estimated digestibility approach. It is likely not necessary to use as many treatments as I did when developing the method. So maybe 3 or 4 different larval density can be enough. And my suggestion is to perform a preliminary trial of the feeding substrate in the first place with a medium density for 10 days. If the survival is good, then you need to assess whether you can separate the larva from the frass easily. If that is the case, you can go with the approach with increasing feeding time. If that's not the case, I suggest you to go with the larval density. And if the survival is low, or if the larvae grow poorly, then my suggestion is to work with these substrates as incorporated in another substrate. So to try it on a mixture with a standard ingredient that you already know the asymptotic estimated digestibility. But this approach means that you need to assume additivity, to assume that the digestibility coefficient is additive. And actually, this is something very important when defining digestibility coefficients, because, as I said in the introduction, one of the reasons why we want to measure digestibility is to use it in a formulation approach. And we want the digestibility to be additive in order for the formulation approach to be reliable. And this is something that still needs to be explored. And there is definitely room for future studies on these aspects to assess whether or not these digestibility coefficients are additive. If that is the case, another aspect is the development of digestible nutritional content of the various substrate that we can use. So that means we could switch from feed table based on crude nutritional contents to feed table based on digestible nutritional contents. So I did it for the 3 diets that I presented you. And this can truly make a difference for more precise and accurate diet formulation, or at least that's what we hypothesize. And these aspects could also be investigated. We assume that should we formulate isodigestible diets, so diets with the same amount of digestible nutrients, we assume that we will have a reduced variability compared to isonutritional diets that I mentioned in the introduction. And there is also room for future research in that field. Finally, this picture shows the process of feed conversion in black soldier fly larvae. I divided it in 5 different steps. Digestibility assessment focuses on digestion and absorption, but of course we should also consider other steps such as ingestion and of course metabolic utilization. And this is something that is often explored in conventional livestock, to go beyond digestive efficiency and to also work on metabolic efficiency. So we definitely need more efforts to be put on the understanding of the utilization pathways of the absorbed nutrients. And there is also a lot of definitely room for research in that field. 2 other aspects that could be perspectives for this approach is to explore the role of the texture, because we assume that the viscosity of the substrate, its water holding capacity, the particle size will have an impact on the ingestion capacity and on the digestibility, of course. And finally, the microbiota of the substrate and of the gut will also very likely have an effect on digestibility. So these aspects should also be investigated in future studies. So should you want to go further, you can find the paper that describes the first approach, the asymptotic estimated digestibility with increasing larval density. The rest of the results that I presented are included in my PhD thesis, but have not been published as papers. So feel free to have a look at it if you're interested in. Feel free to contact me if you want more information on this. And if you were not interested in black soldier-fly larvae, well, thank you for staying until then. In mealworms and orthopterans, so I'm not an expert on these species, but I think there are more straightforward way to measure digestibility because we do not. It's much more easier to separate non-ingested feed, exuviae, and excreta. It can be visually separated. So you have different papers that assess digestibility in these species, and some are very recent. So should you want more general details on digestibility and on nutrition of insects in general, of course, I recommend you to have a look at the bug book chapter on this aspect. And last but not least, the Waldbauer publication from 1968 on different digestibility definitions in insects is definitely worth a read if you want to investigate these aspects. So thanks a lot for your attention. I will be happy to answer your questions. And of course, thanks again to Gerbes and David for inviting me. Thank you.